For those of you who just saw me, welcome back. For those of you who did not just see me, you should have watched the video right before this. So, boo on you. What we're going to be talking about today is, well, again, is failure conditions. Okay? In machine design, we get to use fun words like failure and fatigue and stress and strain. Pretty sure everybody who came up with these terms was really missing sleep. Boy, am I exhausted. Anyways, so we're talking about failure. Why do we need to talk about failure? Well, the important thing about failure is if we understand when failure will occur, we can design such that failure will not occur. Okay? So the whole purpose of understanding failure is you have to design such that failure does not occur. Or you have to analyze a component such that you know when failure would occur. What is the maximum stresses that can be incurred on it? What are the maximum forces? What are the maximum moments that can be transmitted through it? Okay? We can design all of these things if we understand what our failure conditions are. Okay? In order for us to understand failure conditions, we have to talk about the difference between two entities. What is brittle? Okay? Brittle does not mean weak. What brittle means is no plastic deformation. Okay? In malleable materials like metal, when it begins to deform, what happens is the actual lattice inside of there will rearrange. But it will still have contact with the lattice. It will still remain a solid material. Now there are cracks in the material. They will grow, whatever. We'll talk about that later, particularly in grad school. But in a malleable material, a ductile material like steel or aluminum, when the metal begins to move, it does not shatter. Brittle materials like concrete, cast iron, when they begin to reach a high stress value, they simply break. They pull apart, just shatters. Because the lattice itself does not rearrange, it does not grow, it does not flow to allow the material to deform. We do not have any plastic deformation. Everything is elastic deformation. Okay? Until finally fracture. That is a brittle material. Okay? In a ductile material, this experiences plastic deformation. Ductile materials tend to absorb a lot more energy than brittle materials, just because brittle materials, if you look at the stress strain diagram in a brittle material, it may have overall a higher stress strain value, but ultimately the energy that's being absorbed in it is the area underneath this. So for a brittle material, here this is brittle because it only has elastic deformation. In a ductile material, what you have is you may not have as strong of an initial slope, but it begins to do something like this, and the total energy that's absorbed is this distance here. So it ends up being a lot more energy absorbed in a ductile material. Okay, in failure, the theory is that a significant amount of energy is required to cause material to fail. You have a relationship between stress and strain that creates that energy value. The integral of these two, that is energy. Okay, so some people will focus more on stresses, some people will focus more on strains, some people will focus more on energy, and that actually generates a lot of different equations for failure. And people have looked at different material types and they've said, well, this material type behaves best with this failure criteria. And it's kind of gross. This is not, it's not the most beautiful thing. So if you've done your reading for the week already, you know there are 6 different failure criteria that we provide in this book. 6 different failure criteria. Gross. Why don't we just have one? Well, it's because certain failure criteria apply in certain locations. Okay, and part of your reading assignment is how do you know which one to use? Okay. Generally, when it comes down to it, the absolute best failure criterion is, well, I'll write this in this way. So in the last lecture, we had to discuss how to calculate principal stresses. Yes, we're going to be doing that in class this week. Yes, that's going to be an ugly lecture. No, I'm not sorry. Okay, so for ductal failure, which is what we're going to focus on first, which means plastic deformation, the idea is ductal failure. The component yields. Okay, so your failure condition here is SY, which is your yield strength. That is, how far does this go before the component begins to deform? In your vehicle, you don't want any components to deform, because if that happens, all of a sudden all of your mechanisms are out of line. And that will actually cause a very traumatic failure where all of your other components are suddenly stressed and then everything's out of whack and the whole thing blows up. If you have a component that yields when it is not supposed to, whether that be a little bit of a torsional yielding or a bending yielding, it will not have the same kind of integrity that it had before. Okay? You're not, if you have a motor, and on that motor you have some kind of a crank, and this is goes to your crankshaft. If this crank suddenly were to bend, this cannot carry the same amount of load, because now you have a stress concentration that occurs right there. So even a little bit of plastic yielding will cause failure in a ductal system. So this is important for us to consider. Okay? We can't allow this to happen, or else the whole system fails. It doesn't matter that it hasn't fractured. It may never fracture. But if it starts to yield like this, it will not ever be able to carry the same kind of load, and it will ultimately fail. So, when we're talking about ductal failure, we're trying to prevent this from plastically deforming. That's all it is. You have 3 different types of theories that go with ductal failure. You have your max shear stress. You know what? I'm going to go to the summary table. Summary table on page 263. It's high quality stuff. It's got all of the equations. Look at all those equations. So pretty. Okay, and it gives you the page number where you can find them, etc., etc. 263, good stuff. So maximum shear theory, or MSS, the failure criteria is that failure occurs when the maximum shear stress in the system is greater than the maximum shear strength of the system. We do see a lot of metals like steel and aluminum that do fracture in shear. And this is what originated this theory. Now that said, MSS theory does tend to be the most conservative, which means if you calculate the probability of failure or the factor of safety based on the max shear stress theory, you usually will end up overstating how much stress the system can handle, or understating, I guess. So if you use max shear stress and you find out this can handle 10 kpsi of stress, using MSS, then usually your system can handle maybe 11 or 12 kpsi. So it's a little bit more. So this is conservative. It does mean that you can ensure it's not going to fail. One-time loading, 10 kpsi. Now the formula for this is it uses the principal stresses that we calculated in the last class, and it says sigma 1 minus sigma 3, biggest minus smallest. It doesn't even matter what sigma 2 is. Doesn't matter. Divided by 2 is equal to your yield strength divided by your factor of safety. So if you want to know what your factor of safety is, you bring this to this side. N is equal to, oops, sorry, this is 2n. N is equal to sigma y, well, sorry, sy, divided by that equation, sigma 1 minus sigma 3. Okay, this is your factor of safety. What that means is if you know what sigma 1 and sigma 3 are, and you know what sy are, you can figure out what n is. And if you don't like what sigma 1 and sigma 3 are, or if you're picking an n value, you can always choose a different material type with a higher strength to give you a better design factor, okay? Now you can go back and modify the geometry of the system or modify the loading through the system to reduce sigma 1 and sigma 3 if you really need to. But ultimately, this is what maximum shear stress says is the factor of safety for the system. Okay, so next one, distortion energy theory. The idea behind this one is that when a material has absorbed a substantial amount of energy, then it is that material will deform. And whereas this one does not account for sigma 2, this one does. Okay, and it does so by bringing in a new variable called von Mises stress. You should have encountered von Mises stress in mechanics of materials. And if you've ever used SolidWorks, SolidWorks exclusively uses the distortion energy theory, failure criteria, to determine what the von Mises stress is. Doesn't matter what the component is. It always assumes ductile failure. Okay, so keep that in mind. For this, sigma prime, which is the von Mises stress, is equal to sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared divided by 2, and then you take that, then you take the square root of it. So the 1/2 power. I ran out of board space, otherwise I'd have written that 1/2 power nicer. Okay, and there's other equations that are given on 263 for this, but ultimately, yes, okay, great. You can use those equations, and then if you use equation 514, guess what? You don't have to calculate your principal stresses. Huzzah! Save yourself some effort. Okay, and there are special plane stress, yield stress, all of those types of fun things. So that is the idea behind this. Again, just comes in, oh shoot, I forgot. The ultimate equation here is sigma prime is equal to Sy over N, or if you want to know what your factor of safety is, N is equal to your strength, your yield stress, divided by your von Mises stress. Okay, so here's one, this is max shear stress. Here's two, von Mises stress through distortion energy theorem. And the last one is called the Coulomb-Moore theory. The idea behind Coulomb-Moore is what happens here, this SY value is true whether or not it's failing in compression or in tension, which isn't true. A lot of materials like cast iron, concrete, even wood, will not fail in compression, but would fail under tension, or the other way around. Some materials cannot handle compression at all, but can handle a lot of tension load. So what happens when you have a different tension strength versus compressive strength? Okay, so here there are three equations again. Really, this one only ever covers, well, two of them, modified Moore and brittle Coulomb Moore. This page 263 only covers modified Moore, so that's nice. But here it's the equation for modified Moore. Apparently that's the only one you ever really need to use. It has three different failure criteria, and the idea is sigma A is equal to SUT, which is the ultimate tensile strength, divided by N, which is the factor of safety. Okay? And this is only true for sigma A is greater than or equal to sigma B is greater than or equal to 0. Okay? Oh, and apparently it's also true for sigma A is greater than or equal to 0, is greater than or equal to sigma B, but sigma B is smaller than sigma A. Okay, so to recap, if the magnitude of sigma B, which is your second principal stress, is smaller than sigma A, oh man, I'm hoping that this eventually goes back on the live stream. I'm going to have to go back and watch to see if it is actually cutting out. Sometimes the internet here at Doan is fantastic. So I'll watch this video later. I may have to redo those minutes if we truly did miss them. But I'm going to have to keep teaching as it is because yay! So the modified Moore system, again, is the idea is that the principal stress number 1, or this largest principal stress, is equal to the ultimate tensile strength divided by the factor of safety. Okay, where here this principal stress is greater than 0, or as long as this second principal stress, sigma B, has a magnitude that is smaller than sigma A. That's what this is basically saying. Now what happens if sigma B is smaller, but sigma A is still pretty large? Well, then you have this condition, which is where you have to employ both the compression and tension strengths, sigma A divided by C SUT minus sigma B over SUC is equal to 1 over N. And this is only true for sigma A is greater than 0, is greater than or equal to sigma B, and sigma B over sigma A is greater than or equal to 1. Greater than 1, not greater than or equal to. So if the magnitude of sigma B is greater than sigma A, then you have to do this. And then lastly, if A is not greater than 0, you end up with sigma B is equal to negative SUC over N. And this is true for 0. It's greater than or equal to sigma A. It's greater than or equal to sigma B. Okay, so that is modified more. I do believe that is only true for plane stress. 531 is the brittle Coulomb more. Trying to find that equation real quick. It looks very similar to this, it's just less complex. Yeah, so I'll go through a quick example here, and the idea is, let's say we have, so I'm going to go through a problem real quick. So here's the problem. We want a factor of safety n to be greater than or equal to 2. Okay, you want to make sure this thing doesn't fail, so we have an n greater than or equal to 2. We're going to demand that this be well designed such that a factor of 2 applies. Now, in some industries, you may have a factor of safety of 1.1. They get their math calculations tight enough and they know what the input conditions are well enough that they do end up with a safety factor of 1.1. You end up with a safety factor closer to 10 and you're wasting material. You end up with a safety factor closer to 1.1, and at that point you're risking failure if your input conditions are not conservative enough. So you do have those two conditions that run against each other. Either wasting material and making too bulky, too heavy, or on the other hand, you're risking failure if you don't understand your inputs well enough. So that's kind of the dynamic that we have. Here we're going to pick n is equal to 2, really close to 2. We're going to try to get as close to 2 as possible. This is going to give us a value. Now what we have is, we have a geometry that we have for our component that is fairly fixed. I ran into this situation when in my grad school studies when I was designing this component. This component had a stress condition that occurred about right here that I could not change the geometry for this because it was in a very small space. It had to align with existing components well enough. So when I calculated my sigma 1, sigma 2, sigma 3, I couldn't change those values. I was stuck with, say sigma 1 is equal to 22 kpsi, sigma 2 is equal to 18 kpsi, and we'll say sigma 3 is equal to negative 6 kpsi. Okay? I was stuck with those stress conditions. I couldn't change them because I couldn't change the geometry and I couldn't change the loading. I had to go with them as is. So we've got these three stress conditions we can't change, which is unfortunate because we want to get a safety factor of 2, and if we go into, let's say this is ductile failure, we're using MSS, which is the more conservative one. Here n is equal to SY divided by sigma 1 minus sigma 3. Now the challenge with that is we can't change this, we want this, and this is the only other variable in the equation. So what you have to do is you have to select a different material. So what we're doing when we solve this equation is we're going to plug in 2 is equal to SY divided by 22 plus 6, which is equal to SY divided by 28. So what that means is that SY is going to be equal to, is going to have to be greater than or equal to 56 kpsi. So when we go to select a material, we're going to want to make sure that our yield strength for that material is at least 56 kpsi. Now, if we go back to the back of the book, there are a bunch of different material choices in the back of the book. Again, I love the back of the book because there's just so much information that's available. I will go back here and I will find what table that is that says, talks about metals. I'm going to say I want steel. We talked about in the materials chapter why you would pick different materials. For this one, I'm going to pick steel because I like that material. It's fairly easy to machine. Well, it's manufacture. Kind of sucks, but happens. Man, there's a lot of tables. Table, 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 standard pipes. Okay, so I got to A20, and what you will find here is these are different standards for metals. Now you will find that there are some disagreement here between 1030 SAE steel or ASIE steel. There's some difference between 1030 and 1030 over here. Okay, this is just because they come from two different manufacturers, two different testing organizations who independently tested. So some of the values are going to be slightly different. If you pick one, I will be okay with this. But now we need an SY value. So SY value is going to be your yield strength. We need to have 64 kpsi, well 56 kpsi. So we can't use 24. This is a low grade carbon steel. 1020 is pretty common. 30 kpsi, that's pretty normal. If you cold draw it, it's 57. So if the difference between cold draw and hot rolling is that hot rolling, they will pour the metal and it will come out in a bar form or something. It will actually come off of a roll and they will heat it up. Hot rolled metal tends to be more ductile. Cold drawn metal, they take a bar and they push it through a series of molds to shape it down to the exact shape of the metal before they even send it to you. This is at the refinery. Cold drawn metal is not as ductile. It's nowhere near as ductile, but it does tend to have a higher yield strength. So you're sacrificing ductility for strength here. So yeah, you could go and do a 1020 cold drawn 1020 steel, okay? Or you could go with a higher grade. If you want to go with hot rolled, because maybe it's just easier to do hot rolling, you can come over here and say, all right, hot rolled 1080 steel, that'll work. Or we can go on to the next page and talk to more heat treated steel. So this is now what happens after it's manufactured. They will do an annealing process. This is basically they heat it up and then they cool it down specifically. Quenched and tempered, this is where they will heat it up really fast and drop it in water. It causes the crystals inside of the steel to actually realign differently. It's very fascinating. But here we can see just doing quenching and tempering on 1030 steel, which over here 1030 steel is 37.5 to 64. Just by heat treating this, we can get yield strengths that are much higher than what we're looking at over here on this page. So that's good news. If we want to go over here, there are more heat treated steels. Great. These are some tensile tests on some metals. Again, not all of these tables are going to agree because some of these they came from tests from different laboratories, published results. Okay, here's selected steels, where now we're going to be talking about fatigue. We'll get here. Okay, non-steel members. This is cast iron. That's gross. Over here we have aluminum. And then down here we have titanium. Titanium is used in a lot of biomedical applications. So we do have all of those values. If you wanted to pick an aluminum value that has a strength that is greater than or equal to 56 kpsi, you could just pick one. You got to make sure that you write down what the manufacturing method is, what the grade of the metal is. If it's 1020, 1120, 1120 signifies that it has about a 0.2% carbon content, I believe. And then it has some amount of element. Every number in the grade of steel signifies a different chemical composition of that steel, different alloys that are being used in it. But you can pick whatever you want as long as it matches this yield strength. You can do that. Now you'll have to justify to your boss why you're spending so much money on an unnecessarily rough material, but that's up to you. You got to look at the other properties that are available for that steel, and that's really not kind of the scope of what we talk about in this class. In this class we focus most on strength of materials, ductility of materials, those types of things. So we had that quick chapter on why to select different materials, but there are a lot of other decisions that go into picking a material. So, my stomach just rumbled and I have no idea if that went on camera. That'd have been pretty awesome if it did. But, okay. Alright, I'll see you in class this week. Yes, we're going to be talking about this stuff. Yes, you're going to have to know how to calculate these principal stresses. So, good luck. Oh, no! Did show up on camera. Oh, I need to pay attention to that too.